we're going to continue talking about our enolate reactions that we've been so good about studying, right? So we're going to continue on today with the Claisen, which is going to be a similar type of reaction to what that we've done with some of the other like aldol type reactions. We're going to see that in this case we're going to be using an ester, and we're going to be doing our same type of reaction with it using a base. And we're going to end up now with a ketone on it. So we're going to end up, just like with aldol where we had a beta hydroxyaldehyde, with the Claisen condensation you end up with a beta ketone to your ester. So if we consider this to be alpha, that would be beta, right? So with the aldol, we ended up with an aldehyde, and then we had a beta hydroxy group. In this case, we have the ester, and then we have a beta ketone. So remember, alpha, beta are just relative to whatever carbonyl we're talking about. So in this case, we end up with a beta ketone. Beta keto ester would be the, I guess, full name for this thing. But the reaction here is the Claisen condensation, and we're going to see it proceeds much the same way as the aldol, except this time we have a leaving group on our ester. So that's going to allow us to get the ketone. So mechanism, let's take a look at that first. We have our base here. Going to go grab the proton. Going to kick the electrons up. These are always equilibrium. We have our enolate. That is going to come down and find a new friend, an electrophile. So that closes down and attacks another molecule. So note this is right now we're doing a kind of the same molecule one. We can do crossed Claisens as well, and we'll talk about those. Or mixed Claisens as they're called sometimes. All right, so we now have our new bond. We have this ketone or rather this thing is open. It's a tetrahedral intermediate. We had a methyl group, and we had the OET on that. So that's our new carbon there. And simply what happens is we're going to close down our carbonyl and kick out the ethoxide. Thereby doing so, we end up with the ketone now on the other side. So relatively simple mechanism, form the enolate. Enolate attacks a second molecule of your ester. Carbonyl closes back down, kicks out a leaving group, which is your ethoxide. Notice that we are using ethoxide as the base here, and it is getting regenerated in the process, right? So we're making ethanol to deprotonate, and then we end up making another ethoxide at the end here. So we end up regenerating our base. All right, one thing to note about this, by the way, is you must use the base that corresponds with your ester. and it's got to be an alkoxide. So in this case, we had an ethyl ester, so we're going to use ethoxide. If we use hydroxide, we're going to end up just turning that ester into a carboxylic acid, right? If you use methoxide, you'll get transesterification. You'll replace your ETO with MEO instead. So in order to make sure that doesn't happen, when you're doing a Claisen condensation like this, it's important that you use the alkoxide that is the same as your ester. So if you have an isopropyl ester, use isopropoxide as your base. If you have a methyl ester, use methoxide as your base. All right, does that kind of make sense? Because remember, if you try and use sodium methoxide, instead of getting a Claisen, you just replace it. So if you, in the presence of the correct base, you will get the Claisen to happen. All right, alternative. Yeah, go ahead.
I was going to say, if you want the final product.
Yeah, well, then you wouldn't do a Claisen. Or if you said this product, you want this to be a methyl ester. If you want that product, then I would do that at the end. Because then if you do this, you get a mix of products, right? Because some of your because now this proton is much more acidic, right? And you know you're going to end up with a mix of products. So you'll have some that are the ethoxy ester with a ketone. You'll have some with the methyl ester. You'll have some that didn't do anything. So if you want the methyl ester on this, I would then do another step where you use methanol and acid and heat and do a transesterification that way. So you don't have any competing enolate reactions happening. Using the wrong base. Yeah. So if you use, because we have the ethoxide here, if we use a non-ethoxide base, all we end up doing is switching that out. But we saw that if we put this with the ethoxide, we will end up with a very different thing happening, right? So that's the difference there. If you use the wrong base, you just switch it out. If you use the correct base, you get the Claisen to happen. All right. You could probably also get away with using something like sodium hydride with this, because it's non-nucleophilic. It's only a base. But typically these are just done with the conjugate, or just the same thing as your ester. I guess it's a little bit cheaper that way, maybe a little bit safer too. So that works out. All right, so if we want to do a crossed Claisen, or a mixed one as it's called sometimes, we're going to see the same kind of conditions that we considered with aldol for doing a mixed aldol reaction. Option one is have an aldehyde, or have an ester with no alpha protons. So that would be something like a benzyl ester or a formal ester. That would be an example of when you can do the Claisen with. You can also do a formal ester, so formaldehyde ester. If you have one of these as one of your reagents, you can have it present, add your base in, then add your other ester slowly. So let's see what that would look like. Let's say we've got this and so you have to put this one in first with your sodium methoxide. I don't know why I erased that. It's totally okay to write it the other way, but whatever. You have that going, then you add this thing. Notice our first reagent does not have any alpha protons because there's no alpha carbon, right? So there's no alpha protons. So the base is not going to do anything. If anything, it'll just react and just produce the same thing, right? Methoxide would attack, kick out methoxide, no change. So we're okay. However, if we tried to put the base with number 2, it would just react with itself, do a Claisen with itself. So if we want to do a crossed Claisen, we want to have one of our substrates to not have any alpha protons. That's the first option we can do. And so if we choose this option, then we put the one without any alpha protons in first with the base. And then we're going to slowly add this one in. And so as a result, like if you imagine this one is purple, this one is blue. Here's our reaction vessel. It's a lovely Erlenmeyer, isn't it? What we're doing is if we add in drops of blue, we're going to have all of those blues in this sea of purple. So we have all the purple there, all of our formal ester with our base. And as we're adding the blue one in drop-wise, we see that the blue one is much more likely to run into purple ones then, rather than run into other blue ones, if we're adding it slowly. And so if we slowly add our blue one in, the ester that has the alpha protons, it's going to then react with our purple one, which is the aldehyde ester. So as a result, that's a kind of experimental way to make sure that we don't have number 2, the blue one, reacting with itself. All right, so let's take a look. So obviously number 1 is not going to be our nucleophile. That has to be the electrophile because there are no alpha protons there. This is our electrophile. This is our nucleophile. Nucleophile is going to have its proton removed by the base. And again, notice we're using the same base as our ester. Our ester is a methyl ester, so we are using methoxide. Ooh, I'm going to do this arrow like that. I don't want to do this in the middle. I'm going to put this down here. All right, so we have our nucleophile now. It's going to go ahead and find its electrophile friend. Those come down. Enolate then attacks, opens that up. And we're going to go this way. So now we have what used to be our carbonyl. An H. I'm going to put the H down just so we have some space here. We now have this carbon in red. This carbon is now going to be bound here. Right, so that's that carbon, right? It's the one that just attacked the aldehyde. So we have our 2 methyl groups there, and then we have the rest of the molecule, which will be the methyl ester. I'm just drawing it so that we have the correct connections there. That red carbon is the same carbon, so it's the one that has attacked the aldehyde. The aldehyde will close down, kick out the ester, or ethoxide rather, methoxide. Well, methoxide, there we go. And if I were so inclined, I could draw the H. So as we see here, it's much the same, except we have now a defined electrophile and nucleophile. Whereas in the, kind of unimolecular Claisen, or homomolecular, I guess would be a better word, we're attacking the same thing. Our electrophile and nucleophile are the same molecule. With a crossed Claisen, we're going to identify one as our electrophile and identify one as our nucleophile. Our nucleophile will attack the electrophile. The electrophile is going to lose the ester part of it. And so we can do it that way. And we can also do some weird stuff where we don't necessarily need an ester to do this sort of reaction. Our nucleophile could just be a ketone or an aldehyde. The electrophile needs to be the ester. So let's make a note of that. So because our nucleophile, that methoxy group doesn't do anything. So we could use just a ketone if we wanted. It would just change what's on the other half of the molecule. The new bond that's being formed in this reaction is right here. That's the new bond. So we're essentially replacing the methyl ester with the rest of our other molecule, connecting that alpha carbon to the carbonyl of our electrophile, and we have lost our ester. We'll take a look at another one. And in this case, we'll do option 2. So option 1 was have no alpha protons on one of them. Right. Option 2, just like before, is use KH or LDA instead. This will be for cross Claisens, because remember, these will irreversibly deprotonate, and they are non-basic. I'm sorry, they're non-nucleophilic. Non-nucleophilic strong bases, they're going to deprotonate your nucleophile, and you can have it sitting there, and then you can add in your electrophile, and the electrophile can have alpha protons this time. So let's say we want, I don't know, acetophenone and acetone. We want this to happen. We can choose which one we want to be our nucleophile, and we'll have the other one be our electrophile. So with these, we can choose. I want the left one to be our nucleophile. So if I want that to do the nucleophile, I'm going to take it. I'm going to give it our strong base. Doesn't matter which one in this case. So H minus comes in. Forms our enolate. Oh, this one needs to be the ester. What shall we have it be? How about we have it be, let's make this one an ethyl ester. So we've got our nucleophile all ready to go. Remember, this is just going to hang out here until we put in our ester. If we put in our ester, once we put it in, I'm going to come in here, pop open the ester. So now we have this tetrahedral minus. We have our ethyl ethoxide group, and that is ready to leave. Kick it out, and we will end up with our, I guess I'll draw it to the left so we can see it all more clearly. But we have now just combined these two. All right, so really only your electrophile needs to be an ester. So your nucleophile can be any sort of alpha proton containing compound. It could be a ketone, a diketone, a diester, a ketoester, an aldehyde, whatever. Doesn't matter. However, your electrophile must be. And then, of course, you're going to want some sort of acid there to finish this off. Because technically speaking, your ethoxide is probably going to grab the proton here, and it's going to just chill as the electrophile until something else happens. So, as this is here, your ethoxide that's just kicked out over there is going to probably grab this proton, and it'll make you just kind of, you'll just sit there as the enolate until an acid comes along, because you'll definitely need to protonate this later. Because ethoxide is a strong base, right? So if we have that just floating around in our flask, of course this thing is resonating to either carbonyl, so it's extra stabilized. As soon as we protonate this, thing, right, we lost ethanol, by the way. As soon as we protonate this thing, we end up with the enol, which will just tautomerize to the ketone, the diketone. We tautomerize, and then we finally have the ketone. So the acid wash, the point of that, by the way, is the acid wash is necessary. Because you have a strong base in the presence of a relatively strong acid. These things are going to react together. However, your enolate is pretty stable, right? That enolate is stabilized because it can resonate in either direction. It can resonate to the left carbonyl or to the right carbonyl. So just like with the basicity question on the exam on Monday, if you're resonating your lone pair away, it's less likely to be able to react, right? It's stabilized. So we're not going to have this interfering with our Claisen because we have a much stronger nucleophile in the regular enolate, not the diketone. The single ketone is a stronger nucleophile because it's less stable. And because this is more stabilized, it's less likely to react. Once you put your acid wash in there, you're going to end up tautomerizing to form your diketone. And then you're done. Hooray! On a mechanism, yes. On a predictive products, no. Yes. Yeah. So so first step KH with your first one. So let's write this out, I suppose. Okay, so we had our benzyl acetophenone rather. We used KH. Second step, we added this dude, and third step H3O plus. So for any of these Claisens, it's always base and acid are both present in there. So you have your base to get the nucleophile going, and then you have an acid wash at the end. And it just depends what your electrophile is. If your electrophile is just hanging around in there, it just depends what you want to do with it. So cool. Alrighty. So in this case, we made a diketone. So we can do all sorts of stuff. We could do this. I mean, we could have it as an ester too. We could have our nucleophile as an ester. Doesn't matter. Only the electrophile has to be an ester for a Claisen reaction. Alrighty. Any other questions on this Claisen business? Other product again. So notice here what we've added. We've added 2 more carbons, and one of them is a ketone. Here are our 2 carbons that we've added. Alrighty. Let's talk about alkylation then. So we can take this an aldehyde. If we take our alpha proton containing substance, aldehyde, ketone, ester, di of all those, whatever, any sort of mix, a ketal or something, a ketone aldehyde thing, whatever, whatever you have that has the alpha protons, if you treat it with one of your bases, you can give it an alkyl group. Let's say we're going to give it our dear friend, the 2-bromopropane, that y'all did not seem to like. We can do this, and we're going to end up just alkylating that alpha position with our new alkyl group. We're going to form a bond between the alpha carbon and the alkyl group here. And it's much the same. Our nucleophile will be our enolate. Actually, I don't know why I put an equilibrium. That's definitely not, because remember, we're producing H2. We have now our other electrophile, which is this 2-bromopropane. Wow, that carbon had 5 bonds and nobody said anything. Wow. Kicks out the bromine, SN2 style. And then we lose, of course, the bromide. So, and we end up with our product. So it's relatively easy to do. You can alkylate your alpha position using a base and then a some sort of electrophile. So it works out nicely here. All right. So pretty straightforward. Right? Should not be too complicated. Questions on that before we look at it in more detail? let's say we have a ketone now instead. And we do the same thing. If we do it with KH at low temperature, and what do we want to put on here? Ethyl group? Very well. I guess that's a propyl group. That's what we're doing. We're going to see our product will be the following. 1, 2, 3. Yeah. However, if we treat this instead with LDA at room temperature, we end up, that's terribly ugly, but we end up with putting the alkyl group on the other side. Room temperature. What's going on here? When did we see temperature being a consideration when we talked about different products forming? Perhaps two words might come to mind. Oh, and you know what? I totally have the things wrong. Whoops. The KH will give you your thermodynamic product. Yeah, my mistake. The LDA is for the other one. Yeah. Let's think, why would one be favored in certain conditions over the other? And we always remember that thermodynamic products are kind of, when heat is involved. Kinetic products are typically when low temperature is involved, right? Because we want to kind of use our intermediate faster. So let's take a look. We're going to see our kinetic enolate. You have the same shirt as me. Thank you. That's very cool. What was I saying? Oh yeah. Okay, so if we consider this, our enolates that are formed, we're going to end up having one that is going to be more kinetic in nature, and one will be more thermodynamic in nature. Why is this one going to be formed more rapidly than the other one? And again, I've done this terrible thing. Why is this formed more rapidly than this one? Why is that left one going to be faster? Why is that formed more quickly? So how does that make it faster? Yeah, so we definitely have some steric considerations. Awesome. Why else? Sterics is going to be the big thing why we're using LDA for that side versus KH. The reason number one, sterics. Reason number two, if we take a look at our original molecule, why is it faster to get the right side? There's more, yeah. So you have more availability of hydrogens, right? So you just happen to have more of them. So, I mean, if you're going to choose an alpha proton, you have 3 on one side, 1 on the other. Like, just statistically, you're more likely to grab one that's equivalent if there's 3 equivalent hydrogens. So sterics, and then the fact that there's more hydrogens will get us to the kinetic intermediate here. So, of course, this LDA is bulky. The enolate on the right side, the double bond on the right side of the molecule is the faster one. Yeah. So the LDA is bulky, so it's obviously going to go to the less substituted side. That's reason one. And then, of course, we have more hydrogens available. And so as a result, we're going to end up going to the other side. All right, so works out nicely. So we have our LDA at low temperature. That'll get us the kinetic product. With KH at room temperature, we're going to say that, of course, this is more stable. This is the more stable enolate because it's more substituted, right? We have a tetrasubstituted double bond that is more stable than having it terminal like the kinetic intermediate one is. And so here we're looking at the reasons our KH is very small. So it has no problem with sterics. It can just go right back in there and grab the proton. And number two, this is our more stable enolate because it's more substituted. So our kinetic product is formed because of steric considerations and the fact that there are more hydrogens. So just it's more likely to form quickly. But at low temperature, we don't really give it enough energy to intermix, to go backwards. And so it's just going to keep the reaction going forward. We're going to react it like this. At room temperature or higher temperatures, we're going to see that we're going to end up equilibrating more to our more stable enolate, giving us our thermodynamic product. Remember, as always, thermodynamic, think that's the hot one. The warmer temperature is your thermodynamic product because equilibrium favors it. The word thermo in there. So you'll want your tiny base, H minus, and you have your more stable enolate, which is favored at higher temperatures. And so as a result, by changing the reaction conditions, you can alkylate different sides of this molecule. You first make your enolate. Your enolate can be on either side. You can choose which side by controlling these conditions. So LDA and low temperature will go to your less substituted side. KH at room temperature will go to your more substituted side. More substituted leads to thermodynamic. Less substituted leads to kinetic. All right? How's that? Does that make sense? Why we would end up with potentially multiple different products here. This also applies for Claisens and aldols too. You can choose your reaction conditions, right? If you're doing a crossed aldol or a crossed Claisen, by using a option 2 in both cases, right, using the super strong base, if you choose your base wisely, instead of using part 2 as propyl bromide, you use part 2 as your ester for a Claisen, or you use an aldehyde or a ketone for number 2 to do an aldol. So really the only difference here is the electrophile. Otherwise, it's exactly the same mechanism that's happening. So it'd all be the same. Okay. Remember that I'm going to just write it out. these conditions still apply for mixed aldol or Claisen. So let's just do an example. So let's choose the same ketone, and let's put it with a different nucleophile this time. And let's do a thermodynamic thing here, and let's put on, how about methylpropionate, and then of course our acid wash at the end. Not necessary for the acid wash for the alkyl halide, of course, because we don't have a ketone to regenerate, so we're okay there. But in this case, we're generating a strong base and all that, so for the Claisen or aldol, we do need that acid wash. All right, so if we're going to do this, we're going to say, well, KH, that's going to give us our more substituted alkene, or enolate, rather. And so that's going to be the one that this carbon here, this alpha carbon, is going to be the one that will attack our ester. So that's where we're going to have our new ketone be attached to. So the rest of the molecule stays the same. I'm going to just put those two methyl groups down. And I'm going to do these in blue just so we can see this. So now we have formed a bond to our blue carbon, and that new bond will be the purple one, the new bond that's formed. All right, so we're forming a new bond there between the purple carbon and the carbonyl of our electrophile. Electrophile will kick out the methoxide, and then we'll be okay with that. All right, if we did LDA instead, low temperature, same ester, we will end up with we'll end up putting it on the other side. All right, so our blue molecule again would be this stuff. And the new bond that's being formed is this one. That's our purple carbon right there. All right. So these conditions still apply for all the others, all the other reactions. So you'll get different regiochemistry depending on your base and temperature choices. But any questions on that? All right. So with this sort of thing, with the alkylation idea, we can also take or do what's called a malonic ester synthesis. This is kind of a combination of Claisen and the alkylation idea. Kind of. We're going to see that we're going to use some sort of halogenated compound. We're going to treat it with typically diethyl malonate, and then we'll use one of our bases. And we're going to end up getting our R group, whatever that happens to be, replacing its bromine or chlorine or whatever with 2 more carbons and an ester. An ester on one of the carbons, the second one. So we will see here that this is added 2 carbons, and one of them is an ester. So we're going from an alkyl halide to an ester with 2 more carbons. So if we were to take a look at an example, propyl bromide, I'm going to call this DEM. That's that first molecule. I'll talk about that in just a second. And then we'll have our LDA. And actually, like, we can put the ester in first and then worry about adding the base in. Okay. And we're going to end up with propyl 1, 2, 3. We're going to add 2 more carbons. The second one has the ester. So we've added 2 more carbons to our molecule, and the second carbon has an ester on it. DEM is diethyl malonate. That's that top molecule there. That is diethyl malonate. That is our reactive species here. So, mechanism. Let's take a look. We have our base. Let's say we're using H- because that's the easiest one to draw. Doesn't matter which side we go up on. Again, this is irreversible. So we now have our enolate. And this is going to go ahead and attack our, the bromide, propyl bromide. SN2 style. Apparently I'm using purple arrows today, so I'll be consistent. X out that. Now here's the interesting part. Now we have 1, 2, 3 more carbons on this. That's from the bromopropane. We've lost our bromide. And so what's going to happen now is we're going to actually hydrolyze one of our bits here. We're going to hydrolyze one of those esters, and we're going to end up, kicking it out as a CO2. So as we hydrolyze this, again, does not matter which side we hydrolyze, because this molecule is symmetrical, right? There's symmetry involved here. We have our carboxylic acid now. And then we just heat this up. We lose CO2, and we end up just kicking out our molecule here. So we have a base comes in, whatever base that shall be. Let's have water come in. Comes in. We're going to end up kicking out our our CO2. We end up with the, I guess technically speaking, it's probably better to take this and make the enolate. That'll be the more stable form of this thing. Oh my gosh. Once we do that, this is irreversible. We have our enolate here. Yeah. All right, we've lost our CO2. This thing is an enolate, which I should indicate. We go ahead and now we're going to go ahead and protonate this thing and then tautomerize back to our product. So we have OH, AT, boop, 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 tautomerize, and we get our product. So we've added 2 more carbons to our bromopropane, and the second of them has an ester. All right, so our original three atoms from the bromopropane are there, and we will have a few more other ones. All right, so we decarboxylate to lose CO2. Losing CO2 gives us just the one ester at the end there. So the point is, with this one, you're going to go ahead and have just one of them. Actually, technically, what am I saying? The other ester should be hydrolyzed as well. It doesn't actually stay as the ester. It's actually going to go to the carboxylic acid. No big difference, right? If you wanted the ester, you can make it. You know how to make esters from carboxylic acids, so you can do that as well. All right, so if you, yeah, I was thinking, like, why am I only doing that on one of them? Cool. All right, so point is, you add 2 more carbons to your molecule. And if you're going to decarboxylate, it's actually going to be the carboxylic acid, not the ester. So I lied to y'all, as I love to do. So just don't forget that it's going to be the acid if you're going to use this hydrolysis part. All right, so you can use this as a means of adding 2 more carbons to a molecule. We know a couple of ways to add 1 carbon, right? That would be using cyanide. Then you can hydrolyze it, do whatever you need to do to mess with it. To add 2 carbons, we have, without the presence of nitrogen, you can do a couple of aldols or Claisens, depending on what type of thing here, or you can do this malonic ester synthesis. And so we have now quite a few ways to add carbons, right? If you want to add 2 carbons, you could do a Grignard. You could do a Gilman. You know, we have a lot of ways to do it now. So add this one to your collection. So quite a few. Say what now? Oh, yeah. Then I need to fix these. You shall have no evidence of my lies. There we go. So first step, deprotonation. Use your strong base to do it. Remember, you were using the strong base here because we want it irreversible, and it'll be kind of the best way to go here. Once we do that, we can go ahead and attack our electrophile. We end up now having the alkyl group added to our diethyl malonate, hydrolyze it, and then we're going to decarboxylate. Decarboxylation ends up giving us an enolate. The enolate can grab a proton and then tautomerize to the acid there. So 2 more carbons added. Cool. You would want to show the decarboxylation. You mean hydrolyzing the esters? Yeah. So I mean, since that's stuff that's from last time, right? So, no, because that's going to take forever. That's like all these more steps to do that. So that's 7 steps, right, to show that. So I'm okay if we skirt that. Mm-hmm. Yeah. Yes, you can. Ta-da! The magic of words. So saves you that couple of steps. Either one. Oh yeah, I realized I did not put or here, did I? There we go. So either one will work. Doesn't matter. Since yeah, KH is easier just because it's fewer letters and it's just H minus, so it makes it a lot easier than diisopropyl ethanamide. Okay, cool. Any other questions on this? All right. Guess what? We can do the same thing with something slightly different. Acetoacetate Ester synthesis. This is essentially the same thing as the malonic ester synthesis. But instead you use some sort of ester, but on the other side it's a ketone. So with this one, same thing. Technically, this will be our second step. Our third step, we're going to want a probably an acid wash here. We're going to get, instead of an acid out, we end up putting 2 carbons on, and we're going to have a ketone now. It's going to make a methyl ketone. Notice we've added 2 carbons, in this case it's a methyl ketone. And this is exactly the same as the last one. We're going to deprotonate, attack, hydrolyze, then do our decarboxylation, and this time we're going to end up with a ketone instead. Because look, here we have the ester that's going to become hydrolyzed. Here we have a ketone. That's the only difference. So I'll show the mechanism. All right, so we're going to have our ester here, whatever it may be. We can have it as an ethyl ester. We'll be consistent. We'll make it an ethyl ester. It doesn't really matter. It's going to be removed anyway. So we're going to go ahead and take out our proton. And go up either side. I'm going to have it go up the ester side because I feel like it. The product will be the same either way, so it doesn't matter which side, which carbonyl you go up. We have our, what did we use, bromopropane. Comes down, attacks, kicks out the bromine. And we have our acetoacetic ester. We have our 1, 2, 3 more carbons added. Hydrolyze. Boom, boom, boom. And now we're going to have our dear friend, the water, come here. We're going to decarboxylate this thing. Decarboxylation loses the CO2. So we are going to have an enolate, just like before. And then 1, 2, 3 carbons there. And then we protonate and tautomerize. Very exciting. So now we have our H3O+. Make the enol. And then tautomerize. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I guess I'll be consistent. 1, 2, 3, 4. There we go. Ta-da! And then we have our ketone now. That had 3 more carbons than our original alkyl halide. 2 more carbons than our original alkyl halide. So much the same mechanism, except we have now a fixed side to decarboxylate. That's that losing CO2 step. And then in this case, we end up with a ketone instead of the acid. So, exciting stuff. We can get this to happen as well. Right, so in this case, it's going to add 2 carbons, and it's going to be a ketone. Diethyl malonate gives you an acid on the other carbon. This one gives us a ketone on the first carbon. The malonic ester gives us the acid on the farther carbon. All right, but again, relatively the same mechanism. Gives us a ketone instead. All right, questions on that one? Alrighty. Next reaction then. This is going to be a conjugate addition. So with a Michael addition, which is our next sort of one, we're going to look at now an enolate kind of as our intermediate, even though we're not necessarily doing this with a strong base or anything. We're going to see that for a Michael addition, you're going to have a Michael donor and a Michael acceptor. These things must be conjugated some sort of conjugated thing. Typically, that's something like this, where you have a conjugated unsaturated ketone or ester or whatever you might have. We're going to see that common ones would be, you can have this as an aldehyde, one of the R, B, and H. You can have it be an ester. You can have it be a nitrile. You can have it be a nitro group. Anything that's got a conjugated double bond, CC double bond in there. So you can have it as kind of just generic form like this. You can have conjugated with a nitrile, conjugated with a nitro group. That would work as well. Notice on all of these cases we have conjugation. We have double bonds separated by a single bond. Those will be our acceptors. Those are the things that are going to be attacked. And we're going to see our Michael donors will be kind of more stabilized enolates. So, for example, something like this. That would be a Michael donor. We're looking at things that are stabilized. So things that are extra acidic. So that lone pair is more stable than a single ketone would be because it can resonate in two different directions. We're looking at ones that have anything that will help stabilize it more than just a plain old single carbonyl. You can have a nitro group as well here. We're looking at really anything that you can resonate this in multiple ways. So no ketones, no aldehydes, diketones, yes, dialdehydes, yes, ketonitriles, yes, ketonitro things, yes. All these things that could have multiple ways of resonating. It's got to be extra stabilized. And we're also going to see our dear friends, the Gilman reagents, fall under these categories. And how a Michael reaction works, Michael addition, your Michael donor will attack your Michael acceptor in a 1,4 type pattern. And so a Michael addition is a 1,4 addition. So we're going to add one thing and add a second thing for one thing on carbon 1, we can say, just arbitrarily, whatever we decide to call carbon 1. And then we're also going to add something on carbon 4. So we'll see what that looks like. So if we go ahead and take a look at the context of a Michael addition, we're going to have something like, actually it's probably easier to explain it with the Gilman reagent. So a Gilman reagent, much like a Grignard reagent, it's just a carbon nucleophile. All right, but it's stabilized by the copper and lithium there. So let's say we have this thing as our Gilman reagents. So we have this isopropyl Gilman thing. That's essentially a nucleophile. What's going to happen is, wow, that's terrible. Let's try that again. We attack the conjugated side of this. We're going to attack the position far away from our carbonyl. And we're going to end up resonating this thing all the way to the carbonyl itself. And so if we think here, we've added now this isopropyl business, and we have an enolate. The enolate, this is going to be taking place in water later on. So that's going to just chill there. We have our enolate. The enolate can then, once we put it in, we can add some water or some acid. Guess what? Does our favorite thing. Grabs the proton. So we end up with enol. And so notice this is the 1,4 part of this. So we added one thing. Did I lose a carbon in this? 1, 2, 3. 1, 2, 3. I totally did. Why don't y'all say nothing?
You lost the carbon.
Ah, thank you, Eric. All right, there we go. So we have our isopropyl group there that's on that carbon. That's our blue carbon, we'll say. So we've added the isopropyl group onto that carbon. We've made our enolate. And notice our second atom was added onto the oxygen. So that hydrogen is going to be our other part there. So we have the oxygen. Let's not use blue on that. Our first atom here, this is the 1. That atom there is the 4. That's why this is a 1,4 addition. So we're adding something to carbon 1. Again, we're just arbitrarily choosing carbons 1 and 4. The point is that they are 3 carbons away, or 3 atoms away. Sorry. So we're adding something to carbon 1, something to carbon 4. What we're adding to carbon 4 is a hydrogen. We're going to see the opposite would be if we try to use a Grignard with this, we're going to get 1,2 addition, meaning we're adding things across just one bond. In this case, we have 3 bonds in between. And of course, this thing, by the way, would tautomerize, and we would end up with our aldehyde again. Nope, forgot the carbon. There we go. So we end up tautomerizing. Our aldehyde. So notice this time we've just added as many carbons as were in our nucleophile, in our Michael donor. Our Michael acceptor is the rest of the molecule. It's just a way of adding carbon-containing substituents onto. It's a way of coupling things, right? If we try to do this, by the way, like I said, with a Grignard reagent, instead, a Grignard is not a Michael donor. We're not going to get a Michael addition. Therefore, we're going to end up just going on the carbonyl directly. So if we tried this, if we tried the MIGBR, if we tried the MIGBR here with our conjugated aldehyde, we just attack the aldehyde. Oh, that reminds me, I have a good meme for this, but that'll be later. if we do this, we will just get, what is it, that thing? And with the water, we just end up getting the alcohol. So notice the difference here. Without a Michael donor, no Michael addition takes place, so we just attack normally at our normal electrophilic site, right? And so as a result, we just get plain old Grignard to aldehyde that gives you an alcohol, right? So standard, same old thing. So Grignard is not a Michael donor. And so as a result, you get 1,2 addition. So you add your isopropyl group on one carbon, and then one atom away, you add your hydrogen. That is a 1,2 addition. With the 1,4 addition, we added our isopropyl group on a carbon, and then 3 carbons away, or 3 bonds away rather, we added our hydrogen. So that is a 1,4 addition. And that's what you're going to see happening with Michael additions. Let's take a look at them together here. So do we see the difference? We are adding in different positions depending what reagent we use. And so Grignard and Gilman are pretty similar reagents, right? But because it's stabilized, it's going to be able to attack the conjugate position instead, yielding the 1,4 product over the 1,2,1.
Can you put the dots
The dots. Oh, okay, I know what you're talking about, yeah. Dot. And then our H is the other bit. Right? I mean, the oxygen is the second atom. 1, 2, 1, 2, 3, 4. So the oxygen that grabs the hydrogen is the fourth atom, relative to our first atom, where we actually make the attack happen. So again, 1, 2, 3, 4. We add something to atom 1, we add something to atom 4. In a 1,2 addition, we add something to atom 1, something to atom 2. Meaning those are adjacent atoms. And we're going to see that would be the same case with just plain old regular ones. But we're going to have to come back to this because I want to talk about the exam and kind of just, I guess, the last couple of days here. So any more questions on the, we're going to continue on with the Michael addition next time. Yeah. I forgot the H. Yeah, because I erased it because I drew it in blue and decided not to draw it in blue. Yeah, should be there with your acid wash. Cool. All right, so this is what I'm going to do for tomorrow. In the first 20 minutes of lab, so from 9:10 to 9:30, I am hijacking your time. We're going to take a look at the first, something similar to the first problem on the exam. So it seems that a lot of you misinterpreted the directions for that problem. For that problem, I had kind of written out that you were supposed to use 2-bromopropane to show all of your synthetic fragments. And half of you did that, half of you didn't. So, because it's just too easy if you just take your, here, I have the key. We'll switch over to that real quick. We'll take a look. All right, so let's take a look at this. Not that one. Okay, so what I meant by this means you must show the synthesis for several of your reagents starting from 2-bromopropane was that you were supposed to show all the fragments that you're putting together onto this amide, starting all of those from 2-bromopropane and showing how you make all of your intermediates, or not intermediates, reagents. So, for example, like, if you just said, aha, I'm going to make this little amine, and then I'm going to just throw on whatever carbons I feel like throwing on, that's kind of just too easy, right? That's not really a synthesis problem, right? So, not going to work that way. So what I meant was you're supposed to say, okay, well, if I'm going to add this aldehyde, I have to show how that aldehyde is made. And that aldehyde is right here in the key. And then if I want to show how to add that acetate group, I chose to do it anhydride. You could use the acid chloride, just you would need to make sure that you write 2 equivalents of your amine there. But notice I showed how to make the anhydride. So I showed every carbon that's going into my final molecule, I showed where it came from 2-bromopropane. And so what we're going to do tomorrow is y'all are going to do this again. It'll be a different molecule, of course. I will give you I'll give you similar conditions where I'll say like, you must show your synthesis from this or something, or show you can use these building blocks. And then from those building blocks, you must show how you make your reagents. Does that make sense? Yes. So I have a couple options of what I'm going to do with the grading. So it will either be I will average your whatever you'll get on your first synthesis problem and your second synthesis problem. I'll either average those together or just choose the higher grade of the 2 of them and apply that instead. Yes, so it'll be on Canvas. So you'll come to My Canvas. You will, at 9:10, it will pop up as, I don't know, synthesis problem or something. And then it'll be best if you actually submit it where you submitted exam 3. Like, it'll let you do a resubmission or whatever. Just stick on the new synthesis problem there so it's all in one place for me when I come to grade these. So you'll go on Canvas, you'll download the synthesis problem. It'll be just one page. Print it out if you want. Since it's just one molecule, you can just do it on a separate page if that's faster for you. You'll have 20 minutes. You'll do all your synthesis. You'll scan it, take your picture or whatever. You will then upload that on Canvas as exam 3. So you'll go under exam 3. It'll say like late submission or whatever, something like that. You'll have an option to do an additional submission there. And that's what you'll do.